Hello and welcome. Today we're going to be solving Laplace's equation on disk and annular domains. So let's just get a sketch of what we're looking for here. We know that Laplace's equation is uxx plus uyy is equal to 0. And now our domain is going to be either a disk or an annulus. Okay, so let's just get a picture of what we're talking about here. We have u is going to be on this vertical axis, and x and y are here. On a disk domain, of course, you're talking about there's going to be some r here. There's going to be some disk that will for our purposes here always put centered at the origin, and here is the disk like that. Okay, so the idea here, and then of course we have boundary condition will be on the edge, so we could have some boundary condition that looks like this, just for example. And the idea here is at every point on the edge of this disk there's going to be some f of theta now that defines the height of the function that we want to solve here. And of course what we're looking for, of course, is a u on the interior, which we're going to do in polar coordinates here. We want that to be equal to 0, so we want to see if we can find some surface that can connect all of the boundary point values to create some surface in which the Laplacian is equal to 0 in the interior. Okay, so that's the question we want to ask. Now we want to know how do we ask it? How do we actually solve this? Of course, the big thing here is we're going to use polar coordinates. Okay, but before we get started, I also wanted to talk a little bit. We're going to be focused most of our time here on the disk in this video, but I did want to talk about that in another future video. We'll talk also about the annulus, like this. And in this particular case, what you do is you're going to be looking on a deleted. You're going to be looking at a deleted center. So here your D is going to be this annulus, so basically a domain, the set of points between two concentric circles. Okay, there is maybe a third, if you want to call it, which is just going to be an infinite annulus, if you want to call it that, of just so you don't have an outer boundary. All you have is stuff out here going like that, but we're not going to worry too much about that in this video. In this video, I want to focus more on this, and then we'll have a second part of this video that's going to focus on the annular domain. So one thing at a time. So let's get this problem started. We need to figure out, I said we're going to use polar coordinates. So what we have to do, of course, is what we have here written before, Laplace's equation. This is, of course, in Euclidean. So we need to switch to polar, which we have a formula for, and we've derived it in the past. So it's going to be 1 over r, partial derivative of r, with respect to r, partial derivative of u with respect to r, inside that operator there, plus 1 over r squared, the second partial derivative of u with respect to theta. And then we're going to set that equal to 0. So this is the equation we want to solve, subject to the boundary condition. And here we're talking Dirichlet, which is going to be that u at r equals some outer edge, the radius of our disk, comma theta, is equal to f of theta, right? Again, this is going to be a given function. So what we want to do is see if we can solve this equation. All right, of course, the method is we're going to use separation of variables as always. Okay, and just like we've always done, u of r of theta is now going to become p of r times q of theta. And we're going to basically factorize our problem into two components and see if we can work out a solution. All right, let's do this and plug it in. So we have del squared is going to be 1 over r the partial derivative of r with respect to pr times the partial derivative of r times p and q plus 1 over r squared, the second partial with respect to theta of p and q there. Okay, so of course q, in this first one, q is going to factor out, so we're just going to have q sitting out front, and that'll be q of theta. And then what we're going to have is r times p prime to the p prime, okay, quantity p prime there, okay, plus, and now we have here, p is going to factor out, we're going to have a 1 over r, oh, I forgot we need to put that 1 over r out there, sorry, on the first term, sorry about that, 1 over r squared, and then we're going to have a q double prime, and we're going to set that equal to 0. Now we're going to do the separation part. Like always, we're going to divide by p and q down there. And then we're going to get 1 over r times rp prime, all quantity prime, plus q double prime over r squared, and that's going to be equal to 0. Oh, we forgot the p is going to be down there, and there's still a q down there. The next thing I want to do is I actually want to multiply this whole equation by r squared, and that's just to get those r's out of the denominator, and we're going to do that, and then we have r p prime, quantity p prime, all over p, times r plus q double prime over q, and that's equal to 0. All right, so here we can now separate, and we'll get r times p prime, quantity prime, all over p. So that p equation is looking pretty funky now. And then we're going to have a negative q double prime over q. All right, so now we've properly separated. We have here a function only of r and here a function only of theta. So they must be equal to some constant. We don't know what set of constants is going to be okay. But we have to understand what we're talking about with boundary conditions. Well, there's no obvious boundary conditions here, but we'll try to understand them. First of all, we know that u of r comma theta is periodic in theta, i.e. we know that u of r at 0 is equal to u at r at 2 pi, or any multiple, right? So it must be that q of 0 is equal to q at 2 pi. Right, so that's one, what we call a boundary condition that's periodic. But we can go further. We know it must be true as well that the derivatives must also be continuous at 0. So, sorry, that's theta equals 0 and 2 pi. So we have another boundary condition here. But the derivatives are equal to each other. And we need this because we know this function has to be smooth in all of its derivatives. And we couldn't have any abrupt jumps or anything crazy happening at the first derivative either. Okay, so we have that. But then what about p? P of r? Well, we don't really know yet, but let's see if we can figure this out. In fact, what we're going to do is we're going to first solve the P eigenfunction problem. That's clearly the more complicated of the two, and let's see if we can do it. Let's write it down as follows. So what we have is r times p prime is equal to lambda p. We can, now it's time we actually worked on this and see if we can simplify it a little bit. What we have here is a product rule. Like so, and that's going to be equal to lambda p. Now let's see if we can simplify this a little bit more, and we're going to distribute in the r to both sides. We have an r squared p double prime plus r p prime equals lambda p. All right, so we don't have no clear boundary conditions. We don't have any clear boundary conditions, but let's see if we can proceed. But note, this is actually a Cauchy-Euler eigenfunction problem. And you might have seen in the previous video that we highlighted this particular one right here as the Cauchy-Euler. So what I want to do is, let's copy that, bring it over to here. And let's recall now what the solutions to. So this is the Cauchy-Euler eigenfunction problem. And it has solutions of the following. So we know that at lambda equals 0, it has the solution P 0a, which is going to be equal to the function 1, and p0b, which is going to be the function natural log of r. And then we also have for lambda, and that'll be lambda 0, and then lambda n is equal to n squared. And we know we have the following: Pn of r is going to be equal to r to the n. And this is for n is equal to plus or minus 1, plus or minus 2, plus or minus 3, and so on and so forth. All right, so we clearly have a sum. We have basically a Pn for all integers, positive and negative. And so we have to keep track of all of that. All right, so in order to do that, we have a lot of solutions to get through. So our general solution, well, before we get to the general solution, what we have here are now the eigenvalues, right? We basically have lambda is all integers. So now what we have to do is now let's go look at the Q equation. All right, so what we had here, let's recall the Q equation said we had Q double prime over Q negative is equal to lambda. Well, that means that's going to be equal to n squared. So now what we have is Q double prime n over Qn is equal to negative n squared. We can write that as Q double prime n is equal to negative n squared Qn, like that. All right, and we have periodic boundary conditions. So that means that Q of 0 is equal to Q of 2 pi, and Q prime of 0 is equal to Q prime of 2 pi. Right. Well, we do know a few solutions. So we know that there are very special functions that are periodic, and their derivatives are periodic, and their second derivatives equal something proportional to the negative of themselves. This is clearly trig functions. So what we have here is Qn of theta has to be equal to an cosine of n theta plus bn of sine n theta, right? And it seems like this is the same for both n positive and negative. So we have the same sort of solutions. So what we want to do now is just plug all this together. So now we have to put P and Q together. So what we can do then is we have the following. So first off, we do seem to have a little thing going on here. So so what we have is Q. So UN of r comma theta is going to be equal to r to the n times an cosine theta plus b n sine theta. Okay, and that's going to be for n's that are the positive, right? Then there's u0 r of theta, which is going to be equal to a0 plus b0 natural log of r, because of those are the two eigenfunctions for the 0 case, and that's for n is equal to 0. And then there's going to be u's for the negative n's, and I'll write with that negative there. And these are going to be very similar. It's really just going to be, I can write it with a negative there, and then of course just have n be positive again. Again, that just helps me remember that we're talking about a negative exponent. And now I have to have different coefficients here. I'm going to have a cn cosine. Oh, you know what? I just see I forgot a little something here. I forgot my n's inside my... So there's an n theta there and an n theta there. Okay, so we have a cosine n theta plus dn sine n theta. Okay. All right, so those are all of our solutions, and that's a lot to think about there. What we're going to do is, on the next page, I'll put them all together. So the general solution is going to be u of r comma theta is equal to a0 plus b0 natural log of r plus the sum, n starts at 1 and goes up for forever, of r to the n power an cosine n theta plus bn sine n theta plus the sum, n goes from 0 up to forever again. And these are the negative exponents. Oh, sorry. These are going to be Cn cosine n theta plus dn sine n theta, like that. So there's our full solution. Okay, and this is for any disk or annular domain. These are going to be useful. Okay, so, but this comes with the big caveat. First, on a disk, r equals 0 is included. because we want bounded solutions, we want the function to exist everywhere on the set. Otherwise, you can't take derivatives at certain points and things like that. We need bounded solutions. Therefore, it must be that b0 is equal to 0 because natural log is not defined. And it must also be true that all the negative r exponents, cn and dn, are all 0 as well. So on a disk domain, we have the following. Okay, so that's a much more simplified answer there that will work for any disk domain. So there, of course, we have a boundary condition. We can say u at capital R. Again, we have our disk, and it has some radius capital R, let's say, and we have some function that's defined f of theta around it that's defined as our boundary condition. Of course, that is given at the beginning of the problem. Is going to be a naught plus the sum n equals 1 to infinity of capital Rn, we're just evaluating there, times an cosine n theta plus capital Rn bn sine n theta. Okay, so what we see here is that this, of course, is going to be a Fourier series for f of theta. The only catch here is, of course, we have to rescale our coefficients by capital Rn there to get it perfectly done. So any function that that has a Fourier series, we can find a solution to the Laplace's equation. All right, so that's how you solve one of these as a disk domain. I'll comment briefly on the annulus. Okay, on the annulus, r equals 0 is not in the domain. And here you're going to have boundary conditions on both inner and outer boundaries. So this case is definitely going to be more complicated. We'll have to deal with it another time. So what I want to do instead, of course, is go back to the disk. Let's do an example problem. So we have u of r equals capital R. And we'll say in this specific example that r is just 1, comma theta. We have the specific function of r cosine theta minus 2r sine theta. All right, if that is going to be my f of theta, of course, all we have to do is look at this and figure it out. So we know the general solution is going to be equal to a naught plus the sum, n starts at 1, goes up to forever, and then we're evaluating r at 1, so we end up with an cosine n theta plus bn sine n theta. All right, and all we have to do now is look at the coefficients. We can see clearly that there is a 1 there, and here there's an n equals 1. and here there is a negative 2 as the coefficient there, and a n equals 1 there. So it must be that a naught is equal to 0, because there's no constant term, and then a n is equal to b n is equal to 0 for all n greater than 1 coefficients. Okay, which leaves the final thing, that a1 is equal to 1 and b1 is equal to negative 2. In which case we have a solution, u of r comma theta, which is equal to so I made a mistake. I see my mistake now. I shouldn't have had those r's in there at all. This should have been a 1 and a 2 there. I kind of skipped to the end. So the answer now is going to be r cosine r to the first power theta minus 2 r to the first power sine theta, like that is our solution. Okay, so it might be worth doing a little bit of conversion here. We know that x is equal to r cosine theta, and y is equal to r sine theta, right? So another way to write this in Cartesian coordinates is x minus 2y. And we can ask ourselves, so this satisfies the boundary conditions, okay? And the question is then, does it satisfy the Laplace's equation? Well, of course it does. Any plane equation solves Laplace's equation, because any first power x, when you take its second derivative, all you're going to get is 0 minus 0 is going to be equal to 0. So yes, it does in fact solve. It does in fact solve Laplace's equation. Any plane will solve Laplace's equation. So I hope you enjoyed the solution. We'll do more example solutions for you in a little bit, but this is just a first example to get going. So thank you very much.